longtime Maple user, and so today I want to talk about, well, student understanding is what I really want to talk about. The differential equations is just my favorite topic. It can be replaced with calculus or linear algebra or numerical analysis or God forbid, number theory or something like that. But mathematics is mathematics, and student understanding is hard. And I think that using a tool like Maple is a real asset and really can be very beneficial for that. And I want to give you a little bit of a exposure or history about where I've come from. And it's really interesting that I mean, it's like from the beginning I was destined to be involved with Maple. As an undergraduate in 1982, I came to the Waterloo area for the Shakespeare Festival over in Stratford, and didn't know that was going to be the first of many times that I would be back here, and they've all been good visits. At the same time, I was taking my first course in differential equations. And my memory of that class was basically the method of the day. New day, new method. And you just learned method after method after method for more and more narrowly defined groups of equations. And as an undergraduate, I loved it. Because I was good at those kinds of manipulations and I could do that kind of stuff. And I could integrate and I could do those kinds of things, and this was just fun. And my friends and other fellow students, you know, we all know what DiffEq stands for, right? Difficult equations. And, you know, it was really frustrating for them. Now, did I learn much in that class? Or did I really just practice my calculus skills? When I got to graduate school and I was a TA for differential equations, I was happy about that. And that was my first time I got exposed to the Boyce and DePrima textbook. I was at Carnegie Mellon University, and both Boyce and DePrima had their degrees from Carnegie Mellon. They were long gone when I was there, but their book was being used, and I just loved that book for the conceptual understanding and presentation of things that I saw. Oh, then I really got to like differential equations just because of the content in the mathematics, not because of the manipulations. 1994. Fast forward, so I had my degree. I was already at the University of South Carolina, and I'd been using Maple again since the mid '80s as well. Some of the people there at Carnegie Mellon had been students at Waterloo and had been working with Maple and brought this thing down there. And boy, it was, you know, I was in love. It was love at first sight for me. All those ASCII plots and all that kind of stuff. But I was like, again, I loved it, but I couldn't see how the masses were going to use it because, I mean, there was no computer system had an interface back then. But you know, it was just, you know, you had to really like it to play with it and to use these tools. But you know, in the early '90s, when the interface started to come up, you could do graphs and things inline, and you could do more things interactively or see things more mathematically. You know, those old ASCII equations with all those vertical bars and slashes to make parentheses and all these things were just, I mean, that was an art. So, but today's students don't understand what I'm talking about, but many of you will. So. But as the interface developed, I could see this becoming more of a tool for education. And that's really probably been the overriding focus of my entire career since then, has been finding ways to use Maple and computer algebra ideas in educational purposes. Still doing some different kinds of research and different things with differential equation, even helping colleagues implement some number theory and factorization algorithms and other things along the way. But differential equations has always been at the heart of my interests. 1994 also was one of the, I think maybe one of the first, probably was the first Maple summer workshop that I went to, what this conference used to be called. And it's unfortunate that there's so many experienced users here today, because I went there and met Mike and Mike Monaghan and probably Laurent as well, and others of their type that were around, who were the Maple gods to me. And I heard other people asking questions, and I knew how to answer some of them. And that's where the community was always very supportive and encouraging to new users and welcoming. And no one was ever made to feel worse or not welcome because they hadn't been involved in the creation of Maple from the beginning. But I'm getting a little sidetracked here, but still, these events, I didn't know when I met Bill Boyce, and I knew their book, I'd used their book, but I didn't know that now I'd be standing here as now I'm a co-author on that book. As Bill is looking to move out of it, they've asked me it's now Boyce to Prima and Meade, and what they're looking to do, what Wiley wants to do with that, is make this book really in the 21st century, make it dynamic, bring the graphs to life that are in the book, bring the differential equation, because somebody this morning said, maybe it was Lance, said that calculus is dynamic. It's motion. You've got to be able to see it. Well, differential equations is really dynamic. You got to be able to see it to understand what's going on there. And I think that's what I want to be able to bring to my students. Also at I think the 2002 Maple Summer Workshop, I gave a presentation about some work I was using CGI scripts to interact with Maple, making a CGI script interface, web interface for students to enter a problem, send it off to Maple, and get the result back on the web page. And I met somebody else there who was doing the exact same thing. That was Phil Yaskin from Texas A&M. And for the next 17 years, we've been working together and doing different types of things. Again, with much more sophisticated tools than we were working with then. And MapleSoft came out with the Maplets package, which is our, now is antiquated technology, but still works kind of well for some of the pedagogical purposes, I want to say. So let's see what some of those things actually are. So the thing that Phil and I did was this Maplets for Calculus package, which now is a collection of 201 different applets for different topics, from pre-calculus through differential calculus, integral calculus, multivariable calculus, some differential equations, and a variety of other things thrown in along the way. That's all available on the web. And if I get over to it, there. Okay, I'm in. This is what the home page looks like now. And so they're all collected into these, 17 different groups here. And so there are all kinds of different topics. If we go into differentiation or go into limits here. Then the subcategories here. So conceptual understanding, just computations, applications of limits and continuity, and then some approximations and things. And derivatives, again, conceptual understandings, you're working with graphs, to various computational stuff, practicing specific rules, or topics here. And so this was, I kind of made the comment, this is why I made some of the comments I made this morning. These are all, and I'll show you in the differential equations context here, the ones that are computational are step by step. You can't go on to a later step without getting the previous steps right. A great quote that I like from Lou Holtz, football coach in the United States there, and otherwise loudmouth, but practice doesn't make perfect. Perfect practice makes perfect. If you practice it wrong, you're not going to do it right in real. So if you're building bad habits while you're practicing, it's not going to turn into good habits. You're going to have to unlearn those bad habits. So we don't let you move on if we see you've made a mistake in the previous step. All right. So I'll show you some of that here quickly. But this is all right. So within differential equations here. The first one I want to show you here is with direction fields. And I do not have any memory of ever seeing or talking about direction fields from my first differential equations course. Now, back in the 80s, the only pictures you were going to have were the ones that were already made in the book. No sane professor would ask a student to draw a direction field. And you certainly couldn't get a picture of one that you wanted to see if it wasn't already in the book. So a little bit of an issue here that these Maplets don't want to launch directly. So if I come down and just get it out of the downloads folder, it'll pop right up. And so here we are. They all are the same kind of structure here. You've got a button to start a new problem, and you can get new problems as long as you want to keep pushing that button and seeing new ones. This is just a simple little multiple choice question. There's a differential equation, and unfortunately that is not going to really get any larger when you try to make it larger. So we have a differential equation, dy dx equals x squared minus y. Which one of those direction fields corresponds to it? Okay, and I don't know. I mean, if I just click on one, I can check my answer. Oh, I got it right. Got lucky. All right, and so I'll go on to.
Is this how you teach them?
No. I have more than 30 minutes to do this. But in a classroom, every one of you is pulling this up, and you've got 30 different ones. Wait, how did you answer your question? What did you look at in this? Where are the slopes positive and where are they negative? Where are they zero? Where are they unbound or undefined? Right? Those are the things you want to ask. And I don't want to take the time to do that. Okay. All of these also have a show button. If you don't know how to answer the question, you can. I mean, it's kind of silly in this multiple choice one here, but you get a little bit of a encouragement to do it on your own next time, and that changes too. So you get some feedback on this. Colors. And so I made a comment about how students can cheat this. If I assign a student to show me that you've done 5 of these correct, here's what you do. You click show, and then you know what the answer is, and now you click check. So now it looks like you entered the answer. And now you print that out with all the green on it, and you get credit for that. So that's why in this form, these are not assignable for a grade.
Don't your students realize that if they don't
No.
understand?
You said think. That's why I said no.
Okay.
Right? They're thinking about if the game is getting points for homework. I mean, there are some that do, yes, but too many of them just play the game for completing the assignment. because they've got their assignment for my class and 4 other classes. They're trying to get them all done. Getting them done is their first priority. I mean, good students, that's part of the battle, is getting them to realize that, yeah, sometimes the fastest path isn't the best path. In terms of, or you're not solving a local optimization problem. That test is a non-local, objective there. So, okay, so this is one. Go ahead.
Is that set of different problems, is that just a fixed list, or is that generated?
They're randomly generated. I mean, you can see they're powers of the rational functions, and there might be 2 terms in there. There are a couple of classes of functions that, there's a group of, in all of them, there's a collection of families of functions that have different parameters, and then you choose different parameters amongst those families. But all right, so that's one. And I got to get back to here. All right, so now differential equation of a direction field. And it honestly doesn't take a student very long to work with one of these things to catch the idea and to understand what's going on, what you can see in a direction field. Okay? Now this problem, same structure, but it's the opposite question. Now you're just going to get one direction field. What's the differential equation? All right? You want to be able to go both ways. They're different skills. Well, they use similar skills to answer the question, but it's a different way of thinking. Do I want to try to answer this one? Okay, so this one, right? So the slopes are all 0 along the y-axis. So when x equals 0, I should get 0. So it's not going to be 2 or 3. Oh, I guess it's got to be 1. So that's the only one that's going to work for that. And when y equals 0 along the x-axis, the slopes are vertical. They're undefined there. So it looks like you just clicked the first one for all of them, right? That's what the 2 examples tell us. So a new direction field. This one is undefined at both x equals 0 and y equals 0. So it's going to be the first one too. It looks like.
Brings up a point which students often fixate on things or pick up on cues that you don't think you're giving.
Well, I certainly hope that that's not going to be the first one. All right, so that's, yeah, that one's the third one here, right? So again, just getting this direction field, being able to have the students understand what direction field and what a differential equation is. And have I talked once about solving a differential equation? I haven't. I will now. All right, but this is what they want to see first. This is one of the things the Boyce and DePrima book does first. The first thing they do is they talk about what a differential equation is, about direction fields, and then we deal about solutions later. And even what I would like to be able to do is to click on that graph and have a solution curve pop up on that. And I think that's still something that Maple struggles with, but I'm sure they're getting closer to.
That's already in there.
It's in there now?
It's a task template that'll do that.
But that's,
Not as a Maple.
I'm sorry?
Not as a Maple.
Yeah, not in this graph it won't. But all right. But well, that would be nice to help to draw the connection there with the solutions and how to see solutions in those direction fields. Okay. So the last one of these that I want to show you then is solving a second. Yes. And I should say, if you look at, if you notice the names on these, a lot of these Maplets were started by students at Texas A&M. Phil would always assign to his students a class project of writing a Maplet. He'd give them the skeleton and the framework and some of the other ones, and they'd modify things. Theirs were never, I mean, we always did a lot of work to polish them up, but a lot of these things were started by students. So this one, solving second order homogeneous linear ODE with constant coefficients, a very standard topic, not a terribly difficult one once you understand what's going on. But here's one of these drill and practice step-by-step problems. What?
I completely understand the first two map. I don't understand why we teach this.
We'll get to that, well, because we can in some ways. But, and I think, well, that's another question, but if we're going to teach this, we shouldn't spend a whole lot of time on it. But students need to practice maybe to understand that it really isn't very hard. And so we can start, we can get a new problem, right? And so we get, right, so these all have, a second order constant coefficient homogeneous equation with initial conditions. And if I want to practice a specific type, I can choose what kind of roots I'm going to have. If I want, I can make it. So right now it's going to have two real roots, but if I want to make it any of them, I can make it arbitrary, and then I can get different roots there. Okay. All right. So, what do you have to do? You have to find a characteristic equation, and I'm not going to type it in, right? If I need to, I have a hint. Tell me how I can do things. Right? What are my roots going to be? I guess I'm going to get r equals 4 and 2 squared. Oh, how about minus 4 and minus? Right? But again, I anything that no, it's r plus 4 squared, so it should be minus 4 and minus 4. Oh.
There's only one real.
No, I didn't. Okay, I didn't. I was supposed to tell it that there's only one real root. I needed to indicate what. Outsmarted myself here, so I needed to identify what case I was in, and then you could see that the answer then changed to what it was looking for. All right, and if I had left this on a set one, I wouldn't be asked it down here because I knew what it was going to be. All right, so then what are the solutions? And the first solution, you type that in, the general solution, and so we have the e to the minus 4t and the t e to the minus 4t. And then now just to find the initial conditions, I need to find the derivative, and then I need to plug those in and come back and find the values for a and b, and then I have my whole solution for what it is there. And now I can also then see what that solution looks like. Okay, and here before we even get the graph, okay, there's my solution. What behavior do I expect to have for this problem? What's going to happen to these? Well, it's going to go to 0. Exponential decay from the negative side, it looks like. And now I can actually plot it. And if I want to, I can change my window and have that all updated there.
Now that I like.
Okay. So yeah, the point isn't just getting the answer, but then also see what this looks like. Yeah.
Sorry to jump ahead, but one of your questions earlier, one of the earlier talks was talking about assessment. And students don't want to play the game unless they get credit. So are you saying that you actually examine the students on things like this?
So there are test questions like this, but I can't ask those questions through this interface.
Yeah,
I don't have this connected up to a grade book.
so they're learning interface skills and what the menus mean and how to navigate through, how to type in an equation in ASCII, all kinds of extra things that are not tested, they're not assessed in your class.
So what do you mean? What's not assessed?
Well, I'm just asking if you,
I give questions like the direction fields.
okay,
I give on a test. I'll give them a question like that. Find which of these direction matching.
through the menus for that.
No.
All of the,
That's on pencil and paper.
that's applet-centric is not tested on.
That's right.
That's just what I wanted to.
That's right. Okay, so this is I've said too much about these, but this is the drill and practice type. This is kind of old-fashioned. I mean, not just the technology with the Maplets, but finding solutions like this. Okay, what I really wanted, so what more recent stuff. So if I come back, I mean, again, why do we want those solutions? Why do we want students to find those solutions? And so I've done a couple of other visualization tools here. One for, well, the one I'm going to make sure I show here, again, with the second order equations. That's why I did that one example there. And let's see if I can, these are on the Maple cloud. Okay, and if I join Robert's Club. Oh, I didn't want to do that. I wanted Maple. So in the cloud, I've made a couple of these down here. Yeah. Okay. So a second order, undamped, motion with periodic forcing function. Well, right now, no initial or zero initial values. All right, so what happens as I change the period of the forcing function? Oh, okay, so I need to solve the homogeneous equation. I need to look for a particular solution, put them all together, apply the initial conditions. No, I don't need to do all that. I need to, look at what happens. Just drag the slider, and what happens? I get lots of oscillations, and whoa, something happened. That one's not oscillating. Well, it's oscillating, but I mean, there's the other ones you see. There's oscillations within the oscillations, but something's different there. Okay.
How do you prompt them to go through the sliding aspect?
Play with it. What happens is that period changes, as that factor changes, right? Now, I am showing also the solutions down here, and you see, right, so right, so right now I'm not exactly at 2, but doesn't take much to realize that when that is, why can't, I thought I had it so it would pop right on 2. Okay. All right, well, it's not.
Set the current position on the right.
Oh, yes. Right here.
I'd actually like to raise another issue.
Yes.
Based exactly on that, which is accessibility. So a lot of these controls require serious manual dexterity.
That's right. That's right.
Can't do it.
Well, and colors and there's a lot of things that are increasingly concerns. But all right, so why is it not taking that? Oh, no, I'm sorry. That's what I was supposed to do, is just change it right there. Okay, and so when you change that, I mean, the solution looks different now. Why is it different? Now you can start to ask students, now you can maybe, why was it different in that case than it was in all the other cases? Where did extra t come from, and where the other, you had two cosine terms, and what happened? Now there's a little bit of a question to go figure out what happens algebraically. Now, the other thing is, in the books, you end up spending a day using trig identities trying to figure out trying to get this in a form where you can see the beats, where you see the periodic amplitude on the driving period. And, I mean, trying to go through that, you just show off your dexterity with trig identities, and students have no idea where you're headed or why you're headed there. But here, now, I don't need to do that really, but I can see what I'm getting. I can see the beats nature of the solution, and I can verify it algebraically if I want to. But I think this is, to me, this is the kind of thing that I'm now putting my attention to and direction to. Interfaces like this that give students a picture of what's happening, and then drive them to do the mathematics to understand why what they're seeing is real, because sometimes what you see isn't real, and understand what's going on. But again, the picture motivates and encourages then the algebraic manipulations that they need to do the analysis to support their observations and their so and again here, if I want to, I mean, well, how does the initial condition change what's happening here? If I change those, right? What does that do to the problem? Okay, I mean it doesn't do much really, right? There's some transient parts of this that come into play, but then things come into the same kinds of things. So this is one I have. The other one I wanted to show I know as my time is running out here. I think I've already got it up. Another one that students struggle, to me, well, I struggled with and students struggled with, is the phase space. Same problem, second order homogeneous, and this is homogeneous now, right? And this one doesn't even show the solutions, but right, the blue picture on the left, right, here's the solution moving through time. Now we can also pose this as a system of two first order linear differential equations in phase space with the variable and the derivative, the velocity as the variables. And then you graph something, you get something, the red graph on the right in that direction field or a slope field. And now how does that curve, that red curve on the right, correspond to the blue curve on the left? Right? And so this was one of my examples of an animation and building these things up. I can build the individual plots up, and now making this an animation is trivial. Once you've built one frame of this, it's trivial to make this an animation. And I think going through a few examples like this, you can see and so if I now make this a -1, I think that's going to change the nature of it quite significantly. Again, I can see what's happening in this solution in both, the temporally and also in phase space. So again, I think a couple pictures like this, and a couple of examples like this, go a lot further than any static picture in a book. Playing with something, seeing what it means, why, what's special about these points where the solution reaches a local maximum? If I get there, I guess, right? That should be where it crosses the axis, where we're now where y, the derivative is equal to 0. Y is equal to 0, right? And so how do I see important points in the phase space and learn how to interpret those types of things? So those are some of the things that I think that I've done with Maple and differential equations. There are lots of other examples and all other kinds of topics that would do similar kinds of messages, but I think being able to put together these types of tools, putting together this embedded component example here is much easier than building the Maplet. And these two examples I'm showing you here are basically copies of one another, right? The basic elements are the same. I mean, the graphs are a little bit different. Is basically all that's really different in those things. But those are some things that I think really can help improve student understanding. And I appreciate all the lectures that Robert has given me over the years about how to do these things, and I still haven't quite jumped on ship with him, but I'm getting closer maybe. And other encouragement that others have given me, challenges and feedback and encouragement, and I hope that will continue for many years to come still. So thank you. And
So is the audience for this typically engineering mathematics?
so for these were designed specifically for our engineering differential equations course. We have a differential equations course for engineers and for mathematicians. My math students need this too.
So the engineering students, so I did vibrations as my PhD in mechanical engineering. And I took vibrations course, a senior vibrations course, where they assumed the material that you were teaching the engineers now. And our instructor, our advisors, began with complex numbers, and the entire class booed him. So it's 150 who booed the instructor when he put a complex number on there. So the question is, do you use complex numbers in your system here? The derivations are often much simpler.
Oh, yeah. I taught the complex analysis class last spring, and that was the theme of the complex analysis class was make everything exponentials.
Yeah,
Everything's exponential, and it is. And so, I typically don't because I don't want to get booed, but I have been tasked to be the course coordinator for the course now, and so I have reached out to the client disciplines because it's not math students that we're teaching in this class, and so what I want to teach them mathematically isn't the final story, and so I'm looking to see what they say, and I'd be happy to have them come back and tell me, do everything as exponentials.
that won't happen. But if you're going to stick to the real, then there's an easy thing that the engineers actually can use, although they don't really know this, which is differential inequalities. So one thing you can do is look at differential equations with slender units.
Right,
and
right.
watch the solutions be trapped between them.
Right.
And that would be something that would be easily seen on a visualization that you've got here.
Yeah.
Minuscule extra effort to do that from what you've got.
Yeah. No. They don't like inequalities in general, but we have to teach them that they're not so bad, and then I think we can show them that they're not so bad. That's a nice idea. Other
Do you explore these components with the students in the classroom, or they're exploring alone, or both of them?
No, so I would start off by showing this to them because there are no instructions. There are no instructions, and how do you know what to do? And so I would start off by doing this, and then I would say, and then give them their homework out of the book that they're gonna have to do, and then say, okay, when you did this, did you look at it? Because this is set up. You can, whatever your problem is of this type, you can enter it in there, and you can see what your solution is going to be. Now, the Boyce and DePrima book does a lot of times ask that qualitative question: what happens to the solutions? Describe the solution's behavior. Students like to ignore that part of the question. but I think but this allows, I mean, you know, I can answer those questions, but that's hard if you're just getting started with this. But I think this gives them a way to be able to do that. They're asking me to wrap up. I know, but they weren't here to get me started, but they're here to kick me out. So, but I understand. So, thank you.